Lucas. Whereabouts in Europe you come from?
Doing a PhD in Munich.
Is that
Yeah.
is it true that in the north you say moi? Yeah, I like moi. I like it very much. But do you say moi moi?
No, that's too much talking.
Okay.
That's how you can differentiate between the tourists and the...
I don't know, but I'm quite a lot of Europe. And I was in France, all my friends were there now. I'm not sure I have really figured out any topic.
We don't talk much.
Good morning again. So we are starting our session. We have now the pleasure to be with us Professor Pedro Camanho. So we are going to continue with this topic of composite materials. So Professor Pedro Camanho is his PhD is in composite materials from the Department of Aeronautics in Imperial College in London in '99, and he's full professor in the University of Porto, and is vice president of the Institute of Science and Innovation in Mechanical and Industrial Engineering in Copenhagen. So he has a huge CV in this area of composite materials. So with no more delay, so I invite Pedro. The stage is yours, so feel free to start. Thank you very much for being here with us.
Thank you, Luis. Thank you very much for the introduction. Like we said, I'm Pedro Camanho. I'm professor of mechanical engineering at the University of Porto. Actually, I just arrived from Porto. And I will talk today about the prediction of fracture of polymer and composite materials across different landscapes. So this is the outline of the lecture. I'll start with this introduction where I'll really try to motivate this type of work. I'll provide you an overview of the main failure mechanisms that we observe in polymer composite materials. I will focus on composite materials reinforced by directional plies. Then I'll briefly present what we call classical failure criteria and something more recent, three-dimensional invariant-based failure criteria that we have recently proposed. I will also address the issue of in-situ strength, so the size effect that is observed and is often neglected in the analysis of composite materials. Then we'll move to damage models, ply damage and delamination, and then to micromechanical analysis. So it's a busy schedule. We'll try to cover all of these in the allocated time. So, of course, you all know that composite materials have been successfully used especially in aerospace, but also in automotive and other industries. But we need to realize that composites are still facing some challenges. So back in 2005, Alco announced their intention to reduce the cost and weight of their products by 20% to defend the position of metallic aerospace structures against composites. Now, to address these and other challenges, at the University of Porto, we have been working among other topics, but my group mainly on three topics. So the first one that I will cover today is on the development of analysis models to reduce the recurring and non-recurring costs associated with the design and certification of composite structures. We also have been working on the improvement of mechanical response of composite structures with respect to the main design drivers. So we argue that composites are not yet used to their full potential. So we need to understand, for example, what are the main fatal modes that drive the design of aircraft structures. And you can see that there's a strong emphasis on damage tolerance, bearing and bolted joints, buckling and crippling. So we need really to think about new ways or new materials that can tackle these drivers. And of course, we cannot just empirically design or think about new materials. We have to recur also to analysis models, otherwise it would be far too expensive and to take too much time. And also, I think composites are ideal materials to use as multifunctional structures. And this is, for example, the IC structure that we have been developing in collaboration with the group of Brian Wardle at MIT. So we have carbon nanotubes that act as a nanosheet heater, and you can see that can de-ice these vertical stabilizers. So, but today I will focus on the analysis models. Now, you can see here in this picture the building block approach used in design and certification of composite structures. So here you can see along the horizontal axis the number of specimens that are used at each stage, and in vertical axis you can see the chronological sequence and the specimen complexity. And you can see here, and also from these pictures, that at the beginning of the product development process, we need to test a large number of very simple couples to get material properties, to screen different materials, and then as we move in this building block approach, you can see that the structural complexity increases, but then the number of specimens decreases. Now the idea there was a setup goal to reduce the time and cost of developing an aircraft structure, say for example a wing, by 20%. So that means that we need to replace part of the physical tests by visual tests, so by what nowadays is called digital twins. So with that, we can reduce, of course, testing costs, and we can also reduce lead time. And another thing that is important is that we can learn a lot about the performance of a given material structure early in the design process, so that will give you more flexibility if you need to change something at a later stage. Now, the other thing that is very important is to be right first time in these expensive full-time tests. Of course, these tests are very expensive, and you don't want to get any surprise. So we need really to support these tests with analysis models. We need to further reduce weight, so we need to challenge current design of some structural details, so we need to further optimize, and to do that we need to have reliable and robust analysis models. The other objective is related with the risk mitigation, so we need to make sure that we have a robust design. So for example, when you certify, say for example this wing, you are applying a set of loading conditions, boundary conditions, and of course during flight the structure will see different conditions. But of course you cannot test for all of them. But you need to understand whether an optimization that was done for this set of boundary conditions and loading conditions is not strongly compromised by any variations in terms of loading and in terms of geometric variabilities and so on. So that means that we need to perform some analysis to check for robustness out of the testing space. And what I've mentioned also before is that when we want to develop new materials, new composite materials, we cannot just make and break and test and empirically design these materials. We need to do that with support of analysis models. Now, but also we need to understand that we have constraints. So, and some of the constraints are the need to have well-defined testing methods for model identification. I think it's very important to have a validated modeling strategy for different structural configurations. So it's of little use something that works, for example, to simulate the bonding of the stiffness panel, but then it doesn't work when you want to simulate impact or compression after impact. So we have to have something that is validated and it works for different structural configurations. And another constraint that is related, of course, with the industrial needs is that we need to have an acceptable simulation time, otherwise we are going to compromise also the design time. So it's very important to develop models that are compromised between accuracy but also in terms of the simulation time and cost. Cost both from the point of view of model identification but also from the point of view of the CQ time. So let me just give you two examples related with these objectives. So the right first time and also the use of these models in failure investigations. So what you can see here is the cryogenic fuel tank that was being developed in the early 2000s by Lockheed Martin in collaboration with NASA to be used in the reusable launching vehicle, the X-33. So when Lockheed Martin pressurized the cryogenic fuel tank, so the tank basically collapsed, so you can see this huge debonding between the face sheet and the core. But the root cause of this collapse were actually these transverse cracks that developed in the composite material that enabled the fuel to leak through the crack. So the fuel, when it reached the core that was at high temperature, basically it applied pressure, it expanded and applied pressure that resulted in this large fraction. So as a result, and according to this NASA publication, this situation turned X-33 from a potentially in space vehicle technology to what that became a $1.5 billion US dollar white elephant to the American taxpayers. Okay, so the NASA canceled the program as a result of this. So, and what is interesting here, this will relate to something that I will describe at a later stage, is that you can see here some thick black blocks. You can see that the microstructure is actually not very good. And you'll see that by using these thick black blocks, we are actually promoting these transverse cracks. So that, at the time, it should have been known by Lockheed Martin. So that's why nowadays there are design rules with narrow plates that can go together. But I'll come back to this issue later. Now, the other important aspect in terms of having these models is to perform further investigations. So this is the structure that collapsed during the American Airlines Flight 587. It was an Airbus A300 back in 2001 that during takeoff, the vertical stabilizer came out. So at that time, okay, so you're not seeing, I will use the mouse then. So at that time, NTSB didn't have really...
Don't worry, because this screen is electronically connected.
Yeah, so I will use this.
Provided that the camera that side.
Okay, yeah. So at that time, NTSB didn't have a lot of experience with composite materials, so they asked NASA for support in terms of the failure investigation. And NASA didn't have really fast tools to simulate a large composite structure, so we were involved in this failure investigation where we developed crystal formulations that link shell elements, so we had to use shell elements there. And with that, we were able to, for example, understand the implications of having some pre-existing defects. We were able to show that the Airbus design was perfectly fine, so that was not the root cause of the accident. So this was very important to give confidence to the pilots and to the clients of this particular aircraft. Before actually Airbus performed physical tests, the lead time was 1 year, so this was done before. So I was not authorized to talk about this for 7 years, but in 2008 we published a paper in the Journal of Aircraft that if you're interested you can add more details in these publications. To use this. Okay, so there's one thing that I'd like to start before we see the main failure mechanism. It's a sentence by Potter that was published a long time ago in the Proceedings of the Royal Society of London, stating that the great success of linear elastic flash mechanics in predicting behavior of isotropic materials has led almost hypnotically to its direct application to composites with little or no modification. So at that time, we're talking about the late 70s, that was an issue, and I think sometimes it's still an error that is made. So we have to, of course, we are using fracture mechanics in the sense that we are studying and trying to simulate mechanics of failure of advanced materials, but we cannot just translate something that was developed for other classes of materials to composites with little or no modification. And this is our challenge. So, like I said, I'm going to focus on laminated composites reinforced by two directional plies, and you can see here the main damage mechanisms that we observe when we load the composite structure. So you can see, of course, that we have separation between the plies, the lamination, so you can see here and there. Then you can also see that we may have cracks within the plies, so we have transverse cracks like here that can be perpendicular to the mid-plane of the laminate, or can be at a different angle. You can see interaction between failure mechanisms, and you can see also that we may have longitudinal cracks, as you can see here, or fiber kinking. Yeah. You can see the picture. Okay, so these are the longitudinal cracks there and there, and these are the transverse cracks. Okay, so with different orientations. And then if we zoom in more detail, you can see here that these transverse cracks correspond to fiber matrix divisions and then cracks propagate through the matrix. Whereas when we have the longitudinal failure, like here, you can see that we have failure of all the constituents. So you can see broken fibers, the matrix is also broken, you have fiber matrix decohesion, and if you apply compression, then you can see these very complex kick bands that Professor Suti studied in his PhD some time ago, right? So, and our challenge is really to develop physical models and then computational implementations, if necessary, that represent this. So you can see that you don't have often one main crack like you move in a metallic structure. You have a network of failure mechanisms that have different orientations that interact in a complex way. And this is really challenging in terms of developing models. But I think one of the key aspects is that you need to understand all these details in order to have models that somehow take into account all these observations. And I'll try to show you how we try to do that, at least when we homogenize composite material. Okay, so let's isolate some of these failure mechanisms, and I'm going to show you some experimental evidence that will guide us then in the development of the models. So the first one is that the fracture angle, when we have a transverse crack like here, of course depends on the applied stress. And of course, if we want to use some fracture mechanics type of approach, at least we need to know what is the geometry of the crack, right? The rotation of the crack. So what we did here was to perform what we call off-axis compression test. So basically you have a UV composite with the fibers oriented at different angles with respect to the compressive load that is along this direction, okay? So this is for 50 degrees, 30, 45, and 60. In other words, we are applying different ratios between the compressive normal stress and in-plane shear stress. So what we can do here is that we use a high-speed camera to identify the fracture angle. So we're looking at the side of the specimen and we are able to capture the fracture angle. And you can see now if you relate the off-axis angle, from 15 all the way to 90 with the fracture angle, you can see that as we have different combinations between the compressive transverse stress and in-plane shear stress, we get different angles. So, and this is something that is important because if then we want to simulate how a crack propagates, you need to know the orientation of the crack in the first place. So this is something that we need to get as baseline information if you want then to use say a continuum damage model. Okay. So the other thing that is often neglected in the analysis of composite materials or in the failure analysis is what we call the in situ effect. That is, I think, easy to understand if we look at this picture. So basically here we have the number of 90-degree plies that are clustered together, or in other words, the thickness of a 90-degree ply block as a function of the stress that we need to apply to create a transverse crack. So here, this continuous line corresponds to the UV strength, okay? And here we have the same material, exactly the same material, but constrained by sublaminates. And you can see that you have this size effect. As you decrease the ply thickness, you are increasing the strength. And that relates with what I've mentioned before in that problem with the Lockheed Martin. You see that they were using very thick ply blocks that promote these transverse cracks at very low strengths. And this is something that we received from Steve's side, from Stanford. So here what Steve did was to test open hole tension. So the same material, same remote stress. The difference is that this is a thick ply, so the ply thickness is here is 0.20 millimeter, and here is a thin ply laminate. So the ply thickness here is 0.04 millimeter. And these are X-rays, so I'm not sure if the picture is very clear, but you can see edge delamination, transverse crack, both from the edges and from the notch. And here, for this very same material, you don't see one single crack. Now, the problem is now if you go to Abacus or to any other software, and you want to predict first ply failure, and you don't take this into account, so you're not going to distinguish between thick and thin. So you're not going to capture this difference in terms of the onset of of transverse cracks. Okay, so this is something that we need to also to take into account if we want to have good predictions of strength in composites. Okay, now also of course we have viscoelastic matrix, so we have viscoplastic effects prior to transverse cracking and of course associated strain rate effects. And here what we did, again, was to perform off-axis tests, but we perform using a split Hopkinson bar and a standard test machine, so a different strain range. So from quasi-static loading all the way to 300 and at a later stage 1000 deformations per second. Now, what we can see here is the relation between the stress and the strain for quasi-static and for dynamic, okay? And you can see that you have this non-linearity that depends on the strain rate that you apply. Of course, this is what we call directional viscoplasticity, in the sense that we usually see this type of response if we were to load the composite material in longitudinal tension, for example, or in transverse tension, it would be brittle. So we need to take into account these effects, these nonlinear effects that may be important depending on the lab, depending on the loading conditions. But there's an additional complexity because this is what we can consider as directional viscoplasticity. Okay? And you can see here, for example, this is just the use of digital image correlation in one of the tests. You can see that we had actually to change completely the setup of the split Hopkinson bar. And actually this is interesting because it relates with what I said before, but because back in the early or mid-2000s, there was a round-robin exercise in terms of high strain rate testing of composites, and the results were all over the place. So some groups claim that there's no effect, other groups claim there's one effect going in one direction, and the other groups have one effect going in the other direction. Now, we realized that often, the oxygen bar setup was being used like it was for a nutcracker metal, right? People press the button, get some curves, and we realized that the results were completely wrong in some cases. So we need to do a lot of work in terms of shaping the poles, in terms of the battle induction, and we obtain now, I think, reliable information in terms of the response at high strain rates. Okay, so this is something that we need to take into account as well. You look at crack resistant curves, both for delamination, especially when you use glass fibers, there's a huge R curve effect, but also for longitudinal failure mechanisms. So you can see here, so if we apply longitudinal compression, so basically what we're doing here it's very complicated to simulate or to obtain R curves in composites, especially for the new generation of composite materials using the compact tension specimens, in my opinion. So we had to solve this problem, but what we did was to came up with a methodology where we relate size effects with the R curves. So we test up to failure different specimens, in this case with two edge notches in tension and compression, and from the size effect law we can get the crack resistance curve. But the bottom line here is that you do get this R curve, and again, the analysis models need to account for the different physical, the different energy dissipation mechanisms that result in these R curves. Okay, so now at university, of course, we like or tend to follow a bottom-up approach. So we like to start in the material and end up in a structure. So often we start at the micro scale, so when we see some examples, we have a discrete representation of all the constituents, fiber matrix and fiber matrix interface. Then we move up in the scales. We can either homogenize, or we can use two-scale finite element models, or we can guide the models for the homogenized composite materials using the information that we get at the lower scale. When they are on one or the other, eventually we have to homogenize to perform simulations at the same subcomponent level. Eventually, we need to move to the macro scale if you want to simulate a large composite aircraft structure, for example. So I think the important thing here is that we use the finer models, so direct numerical simulation, for example, of microstructures, to understand the failure mechanisms, to validate the models that we have developed at the higher scales, and also to guide the models. Okay, to understand it and to get from computational micromechanics, in my opinion, it's very important then to guide and to validate the other models. But if we look at what the industry does, it's actually the opposite, it's the top-down approach. So this is a picture that was kindly provided by Stéphane Bandit from Airbus, where you can see the way that composite structures are designed. So you have a global FE model of an aircraft, you get the efforts to subcomponent, and then you have many structural details. And you need to understand that the industry, they need to perform failure analysis, stability analysis, optimization, they need to calculate safety margins for all these structures, bolted joints, stiffened panels, slide rocks, bonded joints, for many, many loading configurations. Now, and that means that we cannot just solve all problems with nonlinear finite element models, right? It would take too much time. So we need to combine, of course, high fidelity nonlinear finite element models with quick sizing tools, right? So we need either to combine or to be able to develop quick sizing tools without the need to have a sort of surrogate. So often we can do it, in many cases we can. So for example, we'll see in this lecture that, for example, for an open hole tension, we can use fast prediction methods, but if I want to simulate impact or debonding, no. So what we're currently doing, it's not within the scope of this presentation, but also for your information, we are using robust and validated finite element models to generate data, and then we are using machine learning to generate surrogates, then to simulate structural details that we cannot find analytical closed form solutions easily. Okay, so we need to be aware of these two type of approaches. Okay, so what I'm going to do now in the next slides, before moving into damage models and how we simulate fractionally complex structures, I think it's instructive for you to isolate the failure mechanism, to look at failure mechanism one by one, and see from a detailed analysis in terms of the constituents what's going on in the material. You need to have that understanding. You should not just use mathematical representation without understanding the physics at appropriate scales of the mechanisms of failure. So let's consider, for example, a longitudinal tension. So you have stress strain relation over there, linear to failure, but I mean, if you want to test a composite in longitudinal tension, so you'll start loading at values of stress or strain close to the failure load. You start to hear some acoustic emissions, so individual fibers breaking, and then when you have a completely catastrophic failure, you end up with dead that you don't have anything. So it's very difficult to understand from tests what's going on, at least from these tests that I use, for example, following ASTM standards to get stiffness or strength. So what we think we should do is to rely on computational micromechanics to see more detail in a more controlled way all these mechanisms. So our approach is based on four main building blocks. It's 12 of one. So it's we generate the representative volume elements. So with a random distribution of fibers, because distribution is random. Okay, it's not periodic. Then automatically we generate a finite element model. We apply appropriate periodic boundary conditions. We have our own material models for the constituents, for the fiber, for the resin, for the fiber matrix interface. Then we apply the boundary conditions and we run the analysis. For example, if we want to apply transverse compression, we'll end up with this failure plate for fibers. You don't have you have a stochastic distribution for the fiber strength. So you have here for different types of fibers, of carbon fibers, you have the relation between the applied strain and failure probability. So this is the first thing that we need to understand when we want to simulate longitudinal failure, in the sense that I cannot put the same value of strain of the fibers. I have to rely on the appropriate distributions of the particular fiber that the time is. Now, one thing that is often done is the single fiber fragmentation test that you can see here. So you have a single fiber, and then you have the resin, and then you load your specimen, and you can see these individual fiber fractures. You can see, well, of course, it depends on many things. It depends on the sizing of the fiber, it depends on the conditions of the interface, it depends on the resin, but you can have some transverse cracking from the tips of the cracks in the fibers. You can have some interfacial debonding. But the bottom line here is that you have one single fiber and you load it, so you are loading this, in tension, and you can see that the fiber breaks, but then it breaks at different locations, which means that the fiber is fractured and then picks up the load again, and then it develops more and more cracks. So what we can see from simulations and also from other models is that, for example, if you take this position as the position of a fiber fracture, and this is a non-dimensional dimension here, so associated with the axis of the fiber, this is stress. Of course, this is a traction-free crack. Stress is zero there, but you can see that the fiber is picking up stress again. So you have this process, a shear-like process, that reloads the fiber, and that means that then the fiber picks up the load at different locations, and then it has an additional weak spot, and then it breaks, and this continues until it saturates. Okay, so this is just for one fiber, but of course we can simulate this for a composite with direct numerical simulation, where this is a dynamic model because, of course, you have a dynamic effect associated with fiber fracture. So this is a little bit busy, so I will try to isolate the mechanisms here. So, for example, this is one fiber that we took from the fundamental model that broke there. So we have a continuous damage model for the fiber. We are using cohesive elements at the interface, and we have also a plastic damage model for the resin. Okay, so this fiber breaks. So we have this transit dynamic effect associated with the failure of the fiber. We have this stress recovery region that is captured by the fundamental model. We do get some prediction of damage at the interface. And what is interesting also in this particular simulation, we can capture this matrix crack associated with this fracture plane of the fiber, and you can see that then there's a stress concentration at the fibers that are located at the vicinity of the broken fiber. Okay, so we can further look into these effects with another simulation that we have performed, where you can see here, this is our microstructure. So BF means broken fiber, and here you have fibers from 1 to 8, okay? Different positions, random positions. So here, this is time, and this is the stress concentration factor. And when this fiber breaks, so you can see that we have this dynamic effect, okay? So, and this is important because most of the composition micromechanical representations of fiber fracture ignore this. So they are able to capture with a good accuracy this stress concentration factor, but they completely miss this. Because of course you can imagine having a very stiff material under a tensile stress, and then it suddenly breaks, so you have all these stress waves that will propagate. So you can see that these two fibers, 1 and 2, are the ones that pick up most of the load, and the others are reload. So this is the stress on the broken fiber, and then in 1 and 2 as we move along in time. Okay, so this is again along the axis, so the direction perpendicular to the projection. Okay, so now what we already knew from some tests that were done also by Southampton University in the synchrotron is that the failure, longitudinal tensile failure, is controlled by a process of formation of a cluster of broken fibers. And cluster can be whatever you want. So we are using the definition proposed by Jens Wolf from K. Leuven that considers that two fibers are in the same cluster if the distance between the center of the two fibers is lower than 4 times the fiber radius, and the axial distance between the break lengths is less than 10 times the fiber radius. So what you can see is that even from that picture that was obtained using the synchrotron, is that what you get are individual fiber breaks that are not necessarily all in the same plane. They form a cluster, and when the cluster reaches the critical dimension, you get catastrophic failure. And you can capture that from simulation. And actually what I like about this simulation here, or from this representation, is that you can see from computational micromechanics the phenomenon of localization of damage. Because what you see here is stress versus stress strain. And here I have 3 points with 3 colors. And here you can see in a volume, so this is axial position, so it's position along the axis of the fiber, and this is the percentage of broken fibers in one given plane, okay? So you can see that, and you have 3 different strain levels, blue, red, and green, okay? So increasing. So you can see that you are increasing the strain, but in this region, nothing is happening, okay? You don't get more fiber fractures, so all the action is taking place in this region. So you can see that damage is localizing in this region, and you can see exactly that in these pictures here, where you can see, so these fractures are not all in the same plane, but they are in this volume that you can probably see over there, okay? So this is the process, so you can see that you don't have a macro crack that then breaks your specimen. You have fibers that break in different locations, you have a process of cluster formation, and then everything falls apart, okay? And again, from computational micromechanics, we can capture that. Okay, so this is, again, we use the data that was obtained at the synchrotron to further validate the model in terms of the fiber break density with respect to the ply strength, so experimental and numerical. And what you can see here is that we are playing around with the different properties. We are playing around with the properties of the resin. So that means that, for example, we can play around and design new materials without having to make and break the materials. So, for example, we had a project on hybridization of different types of fibers. But before performing the hybridization, we ran simulations to see, and we actually use models to optimize the microstructure. So we can optimize, say, the fiber volume fraction between the different types of fibers and resin, of course. But for that, you need these models, okay? So, and you can see, you can perform analysis, parametric analysis, see what happens if you change shear module of the resin, what happens if you change fiber A to fiber B, and so forth. Okay, so we can study. Yeah.
You're not actually playing, but you are tailoring.
Exactly. So we are tailoring.
Not playing.
Exactly.
It's tailoring.
Yeah, exactly. We are tailoring the microstructure. So the idea when we hybridized was to get a sort of a pseudo-ductile behavior, an additional ductility. Because as you can see there, the response is completely brittle, okay? But by tailoring, thank you, so we can add that, and by optimizing, but of course optimizing needs to have a model to talk with, right? So these are the models that we use. We can design new materials. So this is for longitudinal tension. So for the longitudinal compression, it's very complex. So the material response and the longitudinal compression. I think there's a nice paper from Oren that shows how composite materials deform and fail and the longitudinal compression. So again, stress-strain relation, now in compression. And this is taken from Oren's paper. So if you look at, say, shear stress-strain relation, and these are some simulations that we have run and some experimental data that we have obtained for the resin, okay? Together with Miguel Bessa, that is currently at Brown University. So you can see that in this region where the material is softening, you get this, so we have an additional waviness of the fiber. You don't have perfection in terms of fiber orientation, so perfecting flow in mathematics, right? So you don't get a perfectly aligned fiber, you always get some defect, some misalignment. So when you apply compression, that misalignment will increase and will further load the resin up to a state where you get this fiber bending and rotation. When the resin rehardens, you get this fiber lockup and bend programming until you get this kick bend. So it's, again, when we develop, say, failure criteria or damage models, we really need to take this into account. So what Miguel Bessa and myself did also, together with Camille from Northwestern University, was to, again, run computational micromechanics. So in this case, we have an initial imperfection, so we have some weakness, so that we can also localize damage. We are applying longitudinal compression, so this was a very, very heavy model to run. But the bottom line is that we can actually, so we are applying compression. You can see here the shear stress, here shear strain. You can see the plastic strain, so you can see a region where we have the additional waviness, where plastic deformation occurs, and then you get this instability and the kink band created there. Okay. Okay, so let's move now to transverse tension. So again, you have linear elastic response. You have a brittle failure, but at the low stress, and this is what you get. So you are applying transverse tension, so you are loading in this direction in tension. Again, this is a computational micromechanical model. You get a crack that is in a global sense perpendicular to the loading direction, as you can see there. Okay, so not very complicated in this case. Now, if you apply transverse compression, now you do get this plastic response up to failure, and this fracture plane is not at 45 degrees, which means that it's not maximum shear stress that is creating this crack. Okay, so what we do in collaboration with Thomas Carter. Yeah.
Before back to the previous slide.
Yeah.
So have you identified if the crack, the transverse crack, initiates within the resin band, or is it at the fiber matrix?
It's fiber matrix interface, exactly. So that's a very good point as well, because often you get defects, you get voids and defects, and you can simulate these voids. This is something that is very important nowadays, is to be able to simulate and quantify effects of defects. Why? Because the aeronautical industry is moving to faster production techniques, so they need to produce cheaper costs and at a faster pace. So that means that they need to tolerate more defects, but they need to understand what are defects of defects. So, for example, now with fiber placement machines, you get gaps and overlaps, right? We can simulate gaps and overlaps, but it's very important to understand if you can, or if the aircraft or the safety is somehow compromised with these gaps and overlaps. At the same, at the micromechanical level, we can have some. In this case, we didn't simulate any void, but we could simulate some voids and have the crack starting from a different position. Here it's from the interface.
And but also here it's important how to optimize interfaces and how coatings.
Exactly.
Because obviously, if you resin saying cracks of 8,000 or 9,000 microstrains, so there you have their own interface and cracks initiated 6,000 microstrains or 4,000 microstrains. How the quality is small.
Yeah, exactly. So the interface here is the key aspect here, and in many other cases, I don't know who said that God created the volumes, but the surfaces are not creation of the aggregate. So it's the same here. So and the interfaces again. So now here we yeah, sure.
Are you calculating the compression modulus from this data?
Pardon?
Have you calculated the compression modulus from the data?
We can. In this case, we can obtain the elastic properties, which we did. I mean, for elastic properties, you don't need to go into computational micromechanics. You can use field theory that works very well, or cyanotic model. So you have those for solutions, or you have the mean field theory that it's okay to predict elastic properties. Okay, in my opinion, when it comes to strain, it's more complicated because you don't have the onset of damage that starts in locations that are more prone to develop this damage. Because since you don't have a periodic distribution of reinforcements, you have a weak spot in your material that needs to be captured. Okay, so damage it's not controlled by heat fields; it's controlled by local fields. Okay, so with direct numerical simulation, we can of course get compressive modules or any other property, but we do it mainly to understand that.
Previous page.
Yeah.
Before that.
This one.
Yeah. And if you calculate the compression modulus, which strain data you are using for ductile failure?
Well, for what we do is what you can do is from the final model. So we're talking about the compressive modules. We are in linear regime, right? So it's very easy to homogenize. So you can get stresses, you can get strains, and for that you get elastic properties. Okay. So the problem in terms of homogenizing and getting properties is when you have damage, because it's not trivial to homogenize in the presence of this community. Okay.
Maybe you can show the previous in the previous page the data. Yeah.
This one here.
Actually, bottom of the.
This one.
Yeah.
Okay. No, this is not. No, but this is not for composite. This is for the neat resin. Okay? This is for neat resin. So these were tests that were conducted in. So these are shear tests in neat resin at different strain rates. And we are showing data at different temperatures. So we wanted just to make sure that the models that we used for the resin were accurate. Okay. So, but here what we did, this is an interesting experimental data. So, with some colleagues from Louvain-la-Neuve in Belgium, from the student Jeremy Chevalier and with Professor Thomas Barman, what we did was to use, I'll start here. So this is you can see this is not a simulation, this is an experimental test that was conducted inside SEM, but with a spectrum, right? So we could use the IC, the digital image correlation. So, and from this test, so we're loading the specimen inside the SEM, and we are getting the displacement and strain fields. And we could see, you see the crack at the interface. So I'll play it again. If you look at this interface, this is where the crack will start, and then it will propagate into the matrix. So this was very interesting because I think for the first time we were able to validate computational micromechanical simulations with actual experimental data, because then what we can do is to have this exact representation of the microstructure. So it's not generated by some code where we put fibers at random locations. It's actually the microstructure, and we could get and we learned a lot from this comparison. Okay. One thing that we learned, and well, this is something that probably I do not have the time to go into detail, but for example, classical plasticity models break down in these regions where you have the fibers clustered together. Then in these locations we have to go into a finer scale and use, for example, shear transition zone type of models. Okay, but we got all this information from a combination of these detailed experiments and then with the analysis models. Okay, but like I said, this is something that can be simulated, and you can see here the way that this RV will fail. Okay, and then we can get all these cracks and then unstable crack propagation. Okay, very quickly. So shear, we've seen this. We've seen also from the tests. You get in-plane shear. You get this crack which is perpendicular. You get all these nonlinear response before failure, and transverse shear. You get typically a fracture angle of 45 degrees, which means that it's the maximum principal stress that is creating this crack in this crack plane, so perpendicular to the maximum principal stress. Okay, so this is how the material responds under UV axial stresses. And now we need to simulate, we need to predict these failure mechanisms, okay? Now, of course, what we want to do, there are two things. The first thing is, of course, failure criteria will give you the stress or strain conditions that will trigger the first crack, okay? Now, if you have a UD composite, that will represent the last plane failure as well. It will represent the failure of the specimen. If you have, stress gradients, and if you have multidirectional composites, as normally you have, you need to combine failure criteria with the damage model. Otherwise, you are predicting the first crack, but then the specimen will take higher loads. So this is the first thing that we need to understand. This is something that you need, but alone it's not enough. Then what I'm not going to go into a lot of detail in the failure criteria, especially the classical ones, but this type of division that I do, it's with a purpose, because we have these failure criteria that are associated with failure modes in the sense that you know what was the failure mode, and others that are non-associated with failure modes. And here are interactive in the sense that you use, of course, you want to get a scalar function of stress or strain tensor, right? And you have interactive failure criteria that use more than one scalar component of the stress or the strain tensor, or non-interactive that just use one, like maximum stress or maximum strain. And these are non-associated. Now, I tend to prefer these ones because, if you use non-associated failure criteria, you can do some, analysis, some additional post-processing, but the bottom line is that you don't know from the failure criteria whether you get longitudinal tensile failure, you don't know the fracture angle, and you need that information then to simulate how damage propagates, okay? So I tend to prefer, of course, when we use more complex analysis models, these ones. So starting with the associated failure, non-associated failure criteria, of course, Sci-Hill, so these are polymer failure criteria. I'm not going to go into a lot of detail. You have a scalar function of your stress tensor, and then depending on the way that you define these material properties, the F terms, you get Sci-Hood, Sci-Hill, Aziz, Hoffman, Chavez, and so forth, okay? Now, yeah.
It's also important to explain that many of these criteria are embedded into professional code.
Yes.
And if people don't really understand the assumptions, the implications, the limitations, those criteria, then it can become dangerous because it's really.
Exactly.
And if you don't know where the errors are.
Exactly, there are a lot of pitfalls, and that's a very good point, because there are a number of pitfalls in more classical failure criteria that you need to be aware of. And I'll come back also to this in actually, I think already in this slide. Oh, okay, so this is this is one of the pitfalls. Okay, in this case, this is an associated failure criteria. It's maximum stress or maximum strain, and what you can see here. So we have some test data there. These circles, and in red, this is what we call the line or invariant failure criteria. You can capture this effect that you can see here, which is important. You see, this is the shear strength of applying, right? So if you have moderate values of the reverse compression, this value of the shear at failure increases, okay? So, and of course, maximum stress is not able to capture this effect here. So, maximum stress, there are regions where it's not conservative, and there are regions where it's too conservative, okay? So then you have Ashin. So again, Ashin is in Abacus in other codes. And Ashin, again, you can see that cannot capture this effect. So again, transverse tension and compression versus shear strength. You have experimental points, and Ashin cannot capture this effect over there. So you could argue, okay, it's not the problem because it's conservative, but it's you're going to over-design a composite structure. Okay. Okay. So what I want really to focus is the failure criteria that we have proposed some years ago. what we call it's a fully three-dimensional invariant based on the criteria. And I want to guide you through the process with some of the details, not all. But what we do is let's start with transverse failure, okay? So we want to simulate these transverse cracks, okay? And we take a composite laminate as a transversely isotropic solid with a preferred direction, which is the fiber direction, that is defined by this unit vector A, okay? And with that, we can form a structural tensor of a transversely isotropic solid with this preferred direction, okay? Now, back in the 80s, Jean-Paul Boller demonstrated that the most invariant form of yield or failure surface can be established in terms of the invariance of the stress tensor and of functions that use this structural tensor and the stress tensor as well. Okay? So this is the most general form, and here we can use the stress tensor or components of an additive decomposition of the stress tensor. And this is exactly what later on Spencer did, where he proposed a decomposition of the stress tensor in what was back then called a plasticity-induced component of the stress tensor, P int, and the reaction stress tensor. So P int is formally calculated, imposing that its projection into the fiber direction is 0, and that its trace is also 0. Okay, so with that, what we can do is to propose the three variants that are again scalar functions of the stress tensor that will drive failure. Okay, so the first one you'll see in a moment. This is the first invariant that we propose to capture failure under transverse shear. This one under in-plane shear, and we have to introduce this one here because composite materials are frictional materials, so we do get an effect of hydrostatic pressure in the conditions that trigger failure. Okay, so but you get your stress from your finite element model or some analytical solution, and you just calculate the invariance, and then we get this failure criterion where the invariants here are driving failure, and the alpha parameters are material properties or functions of the material properties that resist failure. So I'll show you, it's very easy to identify the model. So it's like I said, it's a fully three-dimensional model, so there's no restrictions there. And I'll show you how we can identify the model. So let's imagine that you apply in-plane shear. So we are loading your composite material along this line, okay, and to failure, okay? So if I can project the relevant tensors in whatever frame I wish. So I'm using the material frame for convenience, but of course this is based on invariance. I can use whatever I wish. So if I use the material frame, so this is the stress tensor, and this is the unit vector that I use to form the structural tensor. So if I now replace sigma A in the variance, you can see that the only non-zero is I2. Okay? So and my failure criteria results in this simplified expression. So you are loading in this direction, okay? And when you reach failure, you obtain alpha 2 as 1 over the square root of this stress value over there. Okay, and we have alpha 2 identified. Now, if you want to apply now transverse shear, which is more complicated to do experimentally, this is again your stress tensor. A is the same, and now the only non-zero variant is I1. So I do the same as before. When I get failure in the material, I obtain alpha 1 from this equation. So you can see that it's very easy to identify the model. So, but since it's a fully three-dimensional model, of course, we need more tests to obtain relevant material properties. So now in transverse tension, this is the stress tensor. Again, A is the same. And here I have two non-zero invariants. So when I apply the failure criteria, I have one equation and two unknowns. But if I apply now transverse biaxial tension, which is a complicated thing to apply, now for longitudinal failure, which in my opinion is more challenging at this level of representation, the most challenging failure mechanism to capture, So this is what we do. We use this hypothesis that states that fiber heating occurs when the matrix fiber criterion, so the criterion that I just derived, is satisfied in the misalignment frame. So we have what we call this, I'll show you this, misalignment, and when the failure criteria is satisfied in this misalignment frame, then you get the conditions for fiber kicking, because the fibers will lose lateral support and will just collapse. So now what we have to do is just to have a mathematical representation of this hypothesis, okay? So the mathematical representation in principle is simple, because we have two relevant angles there, xi and phi over there, and we can define our unit vector as a function of these two angles, okay? And then we just have, we know the stress state, we have to apply the failure criteria, but we need to know these two angles, okay? So for the kinking plane, so xi is the angle that defines the kinking plane, so we use the hypothesis that the kinking plane is defined by the shear stress that acts here on the transversal isotropic plane. So we can immediately get this knowing the stress state, which is it is convenient. Now you can ask, okay, but how can you validate this hypothesis? When what I can tell is that the alternative would be, for example, to either to run or to apply the failure criteria for several angles, like a brute force optimization, or to use some sort of golden section search to identify. We did both, and it is a very good approximation, you know, for all the validation cases. So we can leave it as it is. We calculate this angle from this expression, so no problem here. Let's see the other one. So the other one is a little bit more complicated, because we have this initial misalignment, but with the stress state, this misalignment will change, right? So we need to calculate the kinking plane as a function of this initial angle, and this one here, that is a function of the shear modules of the resin and of the shear stress, okay? And again, using some basic tensor transformation, we can calculate this component of the stress tensor as a function of these angles. The problem is that I don't know yet this angle there. Okay, so what I have to do is to go into something that I can test and I can represent in simpler terms, which is pure longitudinal compression. So imagine now that I'm applying pure longitudinal compression. So I have this xc angle, which is the kinking angle when I apply pure longitudinal compression. That is this one, that is the one that I'm trying to find, plus the rotation associated with this stress state. Okay, so I know this one here, and I can solve this equation there, and I can linearize this. I don't even need to solve this iteratively, because we are assuming a small angle approximation, so we can have a closed form solution for this one here. So this is what I get from my test data, right? This is a material property, this is a material property, but still I don't know this one here to solve this equation for psi 0. So what I have to do is the following. So what I have to do is to represent and apply my failure criteria for this simple loading condition, okay? So this is the stress state, I calculate the invariance, I apply my failure criteria, and at failure, I know that sigma 1 is equal to my material property, and f is equal to 0, I'm satisfying the criteria. So I get this big equation, but it's a closed form equation, it doesn't matter, it's very easy, which gives me psi c. So you can see, so all these alpha parameters are material properties that I know, and knowing psi c, I can go back, and I can get psi 0, and then I have my failure criteria fully defined. So now the question that you can ask is, okay, how does this work when we compare the experiments? So you can see here, for example, the relation between the compressive strength, the stress, and the off-axis angle. So it's a very simple case. The criteria is working very well. And here, I think this test data is wrong. There's no reason why. You should be careful also with test data, right? So there's also say that states that everybody believes an experimental result except the guy that did the experiment. So be skeptical with experiments as well. So I'm very skeptical with this one, with these points. But you can see that we can capture this effect here, and this is the criteria for fiber caking, right? So, and it's nicely capturing this trend that you can see here when you relate longitudinal compression with implant shear. This is a simple test case that we've seen before, and here this is actually a very complex case. We are relating hydrostatic pressure with these shear stresses. So these are some very complex testing setups, I think, that were developed at Liverpool University, and you can see that we can capture these points quite nicely. And coming back to what Professor Suti said before, with pitfalls, I mean, this is, we can compare the predictions of the failure criteria with some test data in conditions where it's possible to do the tests, but there are some stress states that are very difficult to impose experimentally or are very expensive. For example, if you want to relate in-plane transverse tension and compression with through the thickness tension and compression. So, and since the failure criteria is fully three-dimensional, we can get the predictions, but we don't know, or it's difficult to know whether the predictions are any good. So what we did then, again, was to recur to computational micromechanics. So what we did, since we don't have test data here, was to run computational micromechanics, so applying appropriate boundary conditions in such a way that we are imposing these stress states that you can see here. And so basically what we're doing, we are loading along, you say, this direction, and this is the mean value of a number of RVs that we have run. Okay, so the dots are mean values of computational micromechanical representations. And then, of course, we have to use some anchor points to feed our model, which are the material properties. So this one, that one, that one, and that one, of course, are the properties that feed the model. Okay, and without any fitting, because the computational micromechanical predictions were done by one PhD student, Antonio Melvo, and the criteria was done with Albertino Ortega, another PhD student. So, and then they joined the results, and in red you can see almost perfect correlation. So it was very nice to see this without any fiddling. Now, if you now use Ashin, and this is again related with what Professor Costa Suti said, then you have a problem, because your failure envelope is open. So if you load there, the composite will never ever fail. So if you, and this is in Abacus and other codes, I guess. So, and actually this is an important loading condition, especially in bolted joints, because typically you apply through thickness pressure and then you apply compression in bolt, right? And of course, this is something that Ashin predicts, so it's open. And actually it's not open, it's closed over there.
And if you go back, that vertical fin failure, you had at the beginning of the talk of the Airbus.
Yeah.
That was a compressive failure that started from the bolt.
Exactly, it started from the bolted joint, exactly.
Well, that holds actually, there's one big bolt that holds the vertical fin.
Yeah.
And when that caused the fiber micro-buckling on the composite, the prop floater stably taking away the vertical fin. Of course, the aircraft can fly without the vertical fin, but it happened to occur during takeoff,
Yeah.
which is critical stage.
Yeah. Exactly, it was during takeoff, and you're absolutely right, because it's a bolted joint. It's a big bolted joint, or 6 big bolted joints that they have connected to stabilize it with the fuselage. So yeah, it was. So these complex loading conditions, you can actually see them in relevant aircraft structures. So, but beware with some of the pitfalls that you get in some of the existing models. Okay, so more validation. I will skip this. Okay, so some summary. So this is a new 3D failure criteria with the invariant quadratic formulation that is based on structural tensors. It's an elegant form, I think, because we are not limited to projecting the stress state in a given coordinate system. It's a coordinated system-free description of an isotopic. So I will skip this. The bottom line is that this can look like long equations, but they are closed form. You just need to program these. You don't need to solve equations, okay? So I will skip this and that. Okay, to move because we have 15 minutes left, and I think I was too optimistic in the amount of material, but my plenary lecture tomorrow I will cover some of the things that probably I will leave today because I guess there's no time for everything, so I'll go through the most
Don't
important.
tomorrow, because tomorrow is that Sunday.
Not tomorrow, that's right, it's Monday. It's Monday, yes. Not
You
tomorrow.
said that the wrong place.
Exactly.
They were built in Nigeria.
Yes, it's jet lag from on Monday, okay. It's jet lag from Porto, I guess. So, okay, so let's see the strengths. I've explained this before. So due to the constraints imposed by the neighboring plies, you actually have the actual strengths of transverse plies are higher than those measured in UD coupons, and they increase as you decrease the ply thickness, okay? So these in situ strengths, it's important to note that are not only function of the ply thickness, but also of the fiber orientation or stiffness of the adjacent plies, okay? Okay, so I'm not going to go into details in terms of the way that the models were derived, but this is, in our opinion, it's of course a fraction mechanics problem that we solved using fraction mechanics models. So basically what we do, instead of imagine that you have some sort of analysis models, you have a failure criteria and you have to input some properties like the strengths, right? So what we do is we don't use the strengths that we measure in terms of the in-plane transverse tensile or compressive strength or shear strength, the ones that we measure from UV coupons, because we know that the values are far lower than what we actually see in these materials. We use some fraction mechanics models where the relevant properties are the fracture toughness, okay, the thickness of the ply, and then this is a function of the elastic property. So basically you have these closed form solutions, and what we do is to assign the strength as a function of the thickness. Okay, and we do that for the shear strengths and for transverse tension and compression, okay, with some solutions that I don't have the time to go into all the details, but again, these are closed form solutions. Now, what I would like to show you is really then the use of computational micromechanics, because this was something that was very interesting, because this work was done in collaboration with NASA Langley right after this accident of the Lockheed Martins, because NASA realized that they didn't have the right models to simulate delamination. That's why we worked a lot on squeezing zone models in the early 2000s, and then we realized that okay, the end result was a delamination, but root cause was a transverse crack. So then we had to work on failure criteria, and that's why we start looking in 2005 thereabouts on these size effects and in situ strengths. Without computational micromechanics, that came at a later stage with faster computers and with also developments in terms of modeling capability. So we started with the fraction mechanics simpler solutions, and eventually at a later stage we were able to perform simulations, and simulations are here. So this is from the PhD thesis of Albertino Ortega, former PhD student, now a colleague of mine. And what Albertino did was, so this is a 3D model, but you are just looking at 90-degree ply, so we are loading in this direction, and there's a sublaminate that is not shown here. We just show the 90-degree ply, and we are changing the thickness, you see, going from standard grade to low grade material. So let's load this thing, and remember that we have sublaminate. Okay, so we're going to have multiple cracks, otherwise you only see one. And what we can see here is that from computational micromechanics, again, this starts at the interface. What we can observe, and I'll show you this in a moment, is that the strength that you need to apply to propagate these cracks all the way through the thickness, each higher, when you decrease the thickness. And one interesting thing here that was further validated with some tests that we performed in Grenoble, the synchrotron, that validated this is that if you have, you know, very, very thin laminates, like 20 micron or so, you don't get cracks through the thickness. You get a network of fiber matrix equations. So what you see here is that as you decrease the thickness, the crack density is higher, and probably you understand this from simple fractional mechanics. Why? Because imagine here that you have this large crack, and you have this. Imagine that you have this triangular region there and there. You know, remember from Griffith's analysis, that you have a relaxed stress state, right? So the probability of developing a crack there, it's very low. But these regions are smaller as you decrease the thickness. So here you have a higher crack density because this relaxation is not as pronounced as here. But here you just get a network of fiber matrix equations. Now, what we observed, again, this is from test data, but this was actually in Japan. They were able to perform some nice tests. What we can see here, this is applied strain versus normalized crack length. So this is normalized with the thickness. What we concluded from our analysis that, you know, the strain that creates the first fiber matrix equation is not really dependent on the thickness. It's more on the distribution of the fibers. It's something that results from a local field or a local region where you have the fibers clustered together. It doesn't play a role, thickness, for the onset, but then for the propagation it does. So if you have a thick ply, as soon as you have a fiber matrix equation, it propagates all the way through the thickness, as you can see there and there. If you have thin plies, then you don't propagate the crack through the thickness. Now, and we were able to capture COD, the crack opening displacement, because we get that information from the fiber element model. So the nice thing is that you get all this information from the model. That's what I said before. These computational micromechanics are nice. If the models are good, if the representation are good, we do get a lot of information. So including the crack opening displacement at the fiber matrix equation. And of course, what we see from the finite element simulations is the COD, it's much lower here, and something that you would expect because you have a stiff outer sublaminate that is constraining, right, the crack opening. And that effect is not as pronounced there. And actually you can see from test data that was done in Japan, so these are finite element simulations, this is test data. And for compression we saw the same effect, okay? But for compression, I think where is one, you will get the test data soon, right? So there's no test data yet. So we have the simulations, but not test data. Now, the other thing that we did, so like I said before, so we did this work back in 2005 or something like that with Carlos Davila from NASA, and then we use it since then, but we were only able to validate the fractional mechanics solutions back in, I don't know, 2013, thereabouts, when we ran the computational micromechanics analysis. So we could see these are the fractional mechanics solutions that are shown here in green and blue and red. And you can see the computational micromechanics results, and you can see that there's a nice correlation, so that gives confidence on the models, okay? Okay, now I still have 5 or 10 minutes, so very briefly, probably I can start, or maybe damage models I will address this on Monday, so probably I can either leave the last 5 minutes for questions, or I can use 5 minutes to briefly see damage models. What you prefer? It's up to you. If you want to have any questions, or I can, until 1 o'clock, I know that I can go.
We can choose.
Okay, so I can start with damage models. Yes, that's a nice picture, because it's, okay, yeah, let's see this one. Okay, what you can see here, it's not a modern art painting, it's an open hole tension specimen with a speckled pattern on the surface. So we have a 90-degree ply there. And what we did, and really to show you the importance of and the distinction between first ply failure and last ply failure and the need for a damage model, it will become clear here. So this is actually open hole tension with a 90-degree ply on the surface, stress versus time, experimental. And here, this is the strain field. So this is the field of the strain in the loading direction. And I have plotted two lines there in red and in blue. And here you'll see the strain along these lines, okay? All from digital image correlation, so no simulation there. So what I'm trying to run this. So we'll start loading the specimen, and of course, this one is not very important. You can see the strain. Let me stop there. You can see the strain concentration, of course, from the notch there, okay? And then you keep loading. You can see the strain concentration, and here you get two cracks, okay? Let me stop this. Okay, so you get these peaks of strain that in reality are discontinuity because it's a crack. It's continuity in the displacement field, so it should be a Dirac function there. It's not because this is smoothed out due to digital image correlation. You get these two cracks, okay? So, and you are there, okay? So, the failure criteria will give you this, okay? If you just use a failure criteria, you know your specimen, okay. But then you cannot say, okay, this is the ultimate failure load of my specimen because this is just over 200 megapascal and specimen will fail at over 500 megapascal. So you need then, of course, to identify the onset of damage, but then you need to propagate damage. So let me propagate damage. Okay, it's here. Okay, let's continue. You start to get some edge cracking as well there. You see all these cracks from the free edge. And you get this process of crack accumulation, and eventually the whole thing will fall apart there, okay? So this is what we need to simulate. And you can see that we need to combine failure criteria, that will give the onset, with a damage model. And let's, in the 5 minutes, just show you what was used, I don't know, maybe 20 years ago, but still is often seen in some publications, which is the ply discount method. So basically, you try to simulate, like you see in these pictures, these transverse cracks, and then from some strain concentration that you get from one of these cracks, you may have then fiber failure in a different ply. So what people were doing in the, say, early 90s, late 80s was to use a ply discount method, which is not really, I mean, it's a simplified way to capture this, but with some limitations. So basically you have some elastic property, you satisfy failure criteria, then you reduce this property to a very, very low value. So basically, if you plot stress versus strain, you get this relation, and you can see that for high strains, you get reloading in a free crack, which is not feasible from a physical point of view. So the question is, okay, what are the properties that we reduce to zero or to volumes close to zero? So if you have a transverse crack, so you have a traction-free crack there, so you want these two components to go to zero, so you put these values to zero. If you have a longitudinal crack, you want a traction-free crack with a normal aligned with the x1 direction, so you want these two equal to zero, you put this equal to zero, and this is very simple. So in terms of benefits, you don't need to be an expert in complex programming of damage modeling and all the complexities associated with the complex continuum damage models. This is explicit, so you don't need to be too much worried with conversions of equilibrium equations, but you have mesh dependence. Since it is explicit, it depends on the load increment. You have an ad hoc property degradation, large strains can cause reloading, and you may end up with errors due to improper load redistributions. So what you really need to do to improve on that is to move into more sophisticated
representations of damage. And I'm talking about the lamination, fiber fracture, and transverse matrix crack. And then you need to decide, okay, what is my kinematic and associated constitutive representation of damage? Two things have to be seen in combination. And of course, you can select to represent a crack as a very reliable representation, a strong discontinuity. So if I relate the displacement field with this vertical direction there, and I'm plotting here displacement and here strain, so you have this discontinuity in the strain field for this crack. Here the strain is a Dirac function. You can represent as a weak discontinuity there, so you have a continuous displacement field, but here you have this discontinuity in the strain field, or a regularized localization zone, if you use phase field, for example, where both fields are continuous. So there's no magic bullet here, that some of these representations are better for some failure mechanisms, others are better for others. So you'll see this here, for example. So for micro scale, we use continuum damage models for the fiber and for resin, and the cohesive elements for the interface. Then at the mesoscale, I mean, you can use XFM, but it's difficult to use in my opinion, because you see that you may have different failure mechanisms, and then from a computational point of view, it's very complicated to simulate that in the framework of XFM. I mean, for transverse crack it's fine, but then if you have delamination, fiber fracture, and fiber kicking, then it gets very difficult to simulate. So we tend to prefer continuum damage mechanics. And then for the circle scale, I mean, there's a lot of approaches as well. If you use simple laminates, phase field here works, or it will work hopefully very well, and in some cases we know that it works well. And we can, like I said, use a combination of these modeling approaches depending on the scale that we use. And with that, probably I will stop here, because it's 1 o'clock and Luis wants to stop for lunch, because we have lectures in the afternoon. But like I said, I will be in the conference until Friday, so feel free to contact me if you want to discuss any of these topics. And in more detail, I will continue on Monday.
Yeah, well, thank you, Billy, for your very interesting